Today we start a new, let me turn it off. Yeah, a little better. Yeah. New topic today, part B, efficient polynomial evaluation. Yeah. After 2 lectures this weekend, we are going to have our first quiz, okay, first assignment in quiz format, Canvas quiz. Yeah. So Friday, yeah, I plan to post it on Friday. Okay. All right. So the coverage material, yeah, the first 2 weeks. Okay. Yeah. Part A, 1 topic. Part B. So Part B, we need to use 2 classes this week to complete Part B. Yeah, Part B relatively long and very important. Part B, yeah, because our first programming project will be based on Part B. Yeah. So next week I will assign you our first programming project. Next week. Yeah. Okay. Yeah. All right. B.1, evaluate the polynomials. First, let's look at our problem. Yeah. All right. Our second problem, how to evaluate. So here, based on what I did in the previous class, when we solve that chessboard problem, we talk about one important consideration in this class: solve the problem efficiently, right? Remember, efficiently. Now, in this class, we will emphasize that efficiency a lot. How to solve a computing problem efficiently. All right, let's look at the problem first. Given a polynomial, so our data is a general polynomial in this form. Yeah. General polynomial, okay? All right. The coefficients, all the coefficients are given as an array of data. Okay? Yeah. That's the input. Yeah. But we also need input another value, x value. X is a variable here. So in this polynomial, I need to be careful here. Yeah. Your name? Oh, okay, Jacob. Yeah, all right. Yeah. So the input data, we need a value of x in order to evaluate this polynomial. Yeah. Other than the array coefficient data, we also need a variable value x. Then the question: how to evaluate p of x efficiently? Yeah. Efficiently. Yeah. The first time, we can ignore that efficiently. The first time, let's find the correct value of the polynomial. So everybody here knows how to do it, right? Yeah. If I ask you to write a program to find the correct value of this polynomial, I believe everyone in this class can do it. Yeah, because, what do you need to do? You only need to do additions and multiplications, right? Yeah. Yeah. So if you have some basic programming experience, you can write a program doing additions, multiplications in certain order and find the correct value of it. That's the, first step. So we call it, that's the first step. Find the correct solution. Correct solution. Yeah. All right. Then, when you come to this class, we need to do second step. First step is not good enough. First step is not good enough. Do you know why the first step is not good enough? Yeah. You can find the correct value. In math, no problem. So here, I also talk about the difference between computer science and math. In math, if you can find correct answer, then you're done, right? Why you need to do more, right? Yeah. But in computer science, we have a quite different story here. There is a key difference. Now we're computer science students. So we need to, meet the expectations for computer science people. So what's the extra important consideration we need for computer science people? Other than the correct answer, something is also very important. Think about that. Look at this word. That is important. How long do you need? How much time do you need to find the correct answer? Is that important? If you do it in 1 year, is it good enough? No. The time is very important. Time. Computation time. Execution time. Response time. Extremely important. Okay. So we need to make it very fast. So we want to see our first try, is that a good method? Is that an efficient method? We want to look at that question. So that's our computer science question. All right. Yeah. So let's look at discussion. Here I give you the reference. The material comes from section 6.5. Yeah. So here, let me explain a little bit. So why I, take the material from later chapters in our early class. Yeah. The reason, first, we want to prepare for our first programming project. We want to start our first programming project as early as possible. And this topic is an interesting topic. It's a good topic for the programming. Yeah. Not very hard, but pretty interesting. Okay? So that's the first reason. So I want to jump to this topic first. Second, the background knowledge used, very little. You have the sufficient background knowledge. Because what we are using, basically, additions, multiplications. You're familiar with additions, multiplications, right? Then you can do it. So we don't need more knowledge than that. Yeah. Basic arithmetic knowledge, that's enough. Yeah. So that's why we can do it. We do it early, and it's an interesting topic. Yeah. That's the reason I jumped to that section earlier. After that, basically I will follow the natural order of the textbook. Yeah. After this topic. Now I start from Chapter 2, natural order. Okay? Yeah. All right. First try. Yeah. So, because you already know how to solve it. That's our first try. Okay? Yeah. So we just work on, we apply multiplications and additions. All right. So first, let's look at the multiplication part. We separate. Multiplication part and addition part. Let's separate. Let's look at the multiplication part. When we do multiplications, here we pick up, general term. Yeah, there are many terms, right? There are many terms. Yeah. Let me ask you first question. How many terms do we have here? Can you tell me how many terms do we have here? In terms of n. Really? Yeah, here I use this n, all right? Yeah, n number should be given. Yeah. Here, your answer should be in terms of n. How many? Number of terms. Guess, you know. How many?
Infinite since there's no representation of.
Suppose n is given. N is fixed.
Oh.
Yeah, n is fixed. N number is available. How many? How many? N, yeah. Whatever, yeah, because that's the first guess. Yeah. Any other guess? Yeah. Different from n? Yeah. We already have n guess. Any other different answer? That's our first guess. Yeah. Here, there is a simple counting question. Counting question. Yeah. Because you need to count the number of terms, right? Yeah. But why you feel hard? Yeah. Why you feel relatively hard? Okay. Yeah. If n is given, that's not infinite many, right? Finite many. Yeah. If strictly speaking, we should not say infinite many. Infinite many, we really mean infinite many terms. All right, that's different. Right? Yeah. So here, this part, you know, dot 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 ellipsis, right? This part causes some distraction, right? Or difficulty distraction. Yeah, because when you see this kind of symbol, so you feel, how do I keep track of the data? Right?
So the number of terms that could potentially be represented by the ellipses might as well be infinitely many terms.
Still not infinitely many. Too many terms, but we cannot list all of them, right? That's the meaning of ellipsis. Yeah. Yeah, finite many, but you know, hard to list them all. Yeah, that's the problem. Correct. N plus 1. You fix it. Yeah. Correct answer is n plus 1. Yeah. Other people, other students, can you understand why n plus 1, not n? Why n plus 1 correct, not n? Yeah. No, first term constant, no. Here, nothing to do with the constant or not. Okay? Term, just we treat one term as one object. Okay? No matter constant, variable, it doesn't matter. Okay? Yeah. So nothing to do with constant. Yeah. Just we want to count the number of objects. Yeah. Number of objects. All right? So I delay that a little bit. Yeah. Here, regarding this counting method, I want to introduce a simple, effective counting method. Yeah, I will talk about that later. All right, so here we pick a general term. We use this general term as a representative. Yeah? Because this term can represent all the other terms by choosing appropriate k, right? Yeah. When we choose k equals 0, that's the first term. When we choose k equals 1, second term, and so on. Yeah? So one term we can represent arbitrary term in this polynomial. That's something we frequently use. Yeah. We want to pick a representative to study. When we want to study the properties of a set of objects, so we pick a general representation, representative to study. Yeah. Here, yeah. Now, we want to find the value of this general term. Another question I want to ask you. How many multiplications do we need in terms of k This time k is given. K is given. Yeah. You need to tell me how many multiplications do we need to find this, the value of this term. This term we call the monomial. One term polynomial, so we call it monomial. Yeah. Yeah. Guess, you can guess. Yeah. Make a guess. Yeah. Closed answer. How many multiplications do we need? Yeah, that's one guess. K plus 1. Yeah. Learn from the previous example. At least you learned from previous example. Okay? Yeah. Yeah. That's a, natural, good learning process. Any other answer? Guess? Yeah. Close. Try to make it close. K minus 1, the second one. Yeah. Any other guess? K plus 1, K minus 1. All very close. Yeah. Any other guess? Third guess. Do you want to give a third guess? Don't want to give? Yeah. All right. Nobody wants to give a third guess. Do you want to give a third guess? No? All right. K plus 1, K minus 1. The number in the middle, K. Why nobody makes K guess? Right? Because there is a reasonable guess. Is K a reasonable guess? Right? K is a reasonable guess, right? Yeah. Okay? Yeah. All right. Next question. Now we have, let's say we have three guessed answers. We want to see which one is correct. Yeah. Many times we have this kind of situation. We have several guesses. Yeah. And we want to determine which guess is the correct one. Yeah. In this situation, yeah, now we need to use, this is a problem-solving situation, a typical problem-solving situation. Think about under this situation, in general, what do you want to do? Yeah. Here, remember last time I talked about in problem solving, we need to connect the dots, right? We need to connect the dots. Yeah. We need to make connections, connecting the dots. Here, we need to connect to our real world experience. In our problem solving, we do understanding, right? Yeah, understanding of the problem is extremely important. How do we do understanding? Yeah. One important aspect, we need to use our real world experience to help us do understanding. Okay? All right, here, let me describe a real world situation similar to our situation here. We have three guesses, okay, three different guesses. Yeah. Think about, you get to some new place, okay? You're not familiar with the nearby location, okay? You're not familiar with nearby environment, all right? And there are three different roads. You do not know which one is correct. There are three different roads. In that situation, what do you want to do? Okay? Yeah. Think about it. Go? Google. Google. Yeah. That's one of the strategies, right? Yeah, one of the strategies. All right, so here. I need to quickly get to the point. Yeah. Oh, I forgot to set my alarm clock. Yeah. Yeah. All right. So let me set it now. Yeah. Otherwise, alarm clock. All right. Timer. All right. Yeah. 43 minutes. Remaining 43 minutes. All right. All right. Yeah. Here, in this situation, we need to do some experiments. Yeah? Which one? So 3 guesses, right? K plus 1, K minus 1. All right? All right. Yeah. Do experiments. When we do experiments, yeah. What's the range for this K? What possible values can we choose for this K variable? Possible values. 0, 1, 2, right? Largest one, N. Yeah, so that's the range for this K subscript. K is the subscript of the coefficients. Yeah. All right. In this situation, we want to do experiments on small K values. Small K values. Do experiments. All right. When K equals 0, this term becomes A0, right? How many multiplications do we need to find its value? K equals 0. A0. How many multiplications do you need to do? One term, K, A0 given. A0 given. 0 multiplication, right? No multiplication. You don't need to do any multiplication. All right. K equals 1. What do you get? A1x. How many multiplications do you need? How many multiplications do you need? 1. Yeah, 1. All right. Let's do one more. When K equals 2, how many multiplications? A2x squared. How many multiplications do you need? 2? Correct. Do you have enough information to make conclusion? When K, general K, when you have a general K, how many multiplications do you need? Yeah, subscript. Yeah, the answer? Yeah, the subscript. Subscript is K, right? Yeah. So after you do some simple experiments, can you see K is the correct answer? K is the correct answer, right? Yeah. Yeah. This is a simple strategy. This strategy, very simple, right? Yeah. But in problem solving, many times we need to use this effective strategy. Pretty effective. Yeah. All right? Yeah. This is the first time we use it. Later, we need to use this strategy many, many times. Okay? Do some experiments on simple data. Yeah. You do not need to think about. So here, when you do experiment, do you want to try for K equals 1,376? Do you want to try that? No, right? You don't want to try that. So you want to try the simplest possible data. 0, 1, 2. That's enough. Okay? Yeah. All right. So now, with this strategy, yeah. Now let's go back to our previous question. Do you want to try this same strategy on our previous question, counting number of terms? Counting number of terms. Do you want to try that? Okay? All right. When n equals 1, the polynomial becomes a0 plus a1x. How many terms? 2. When n equals 2, we have a0 plus a1x plus a2x squared. How many terms? 3. Is it enough to make conclusion? What's the answer? N plus 1, right? n plus 1. So the answer of our first question, n plus 1. Is it effective strategy, right? Very effective. Think about that. Yeah. In this class, we will learn many problem-solving strategies. Yeah. This is one of it. Our first strategy. Okay? Yeah. Do experiments on simple data. That's one strategy. Okay? Not fancy, not very fancy, yeah, but very effective. Okay? All right? Yeah. Next. Yeah, so strategy. All right? Now let me erase. Yeah. All right. So here, yeah, so I just repeat experiment. All right? Yeah. Conclusion. K multiplications. All right. Next question. We want to determine if this algorithm is efficient. At this point, we do not have enough information to answer this question. Why? We don't have enough information to answer if it's efficient or not. Because we only know one way to calculate polynomial, right? We only know one way to calculate polynomial. We cannot compare. If we have more than one different ways to calculate a polynomial, then we can do comparison. Which one is more efficient? Which one is less efficient? But here, all of us, we only know one way. We cannot do comparison, so we do not know if it is efficient or not. All right? Yeah. So in order to answer this question, we need to get more information. More information. Yeah. All right. Yeah. But there is another question. Yeah. To get more information. Yeah. That's the first thing. Yeah. We recognize. But second thing, in order to do the comparison of different methods regarding the efficiency, yeah, because here we are studying efficiency. Efficiency, okay, all right. But the question is, how do we measure efficiency, right? Efficiency, we may need some measurement, right? Measure efficiency. How to measure efficiency, right? That's another question, okay? Yeah. If you do not have measure, when you talk about something efficient or not, that would be usually pretty subjective, right? Yeah, subjective. Yeah. Yeah. Some people may feel it's very efficient, but other people feel not efficient, too slow. Yeah. So for that reason, we may like to have some specific measure to, using some appropriate numbers to tell us if it's efficient or not. Yeah. All right. But what number is appropriate for efficiency measurement? Yeah. What number? Yeah. Performance number. Well, what number that can tell us if an algorithm is efficient or not? Yeah. Yeah. You jump pretty fast. Yeah, time complexity. He used the terminology, so we haven't learned. Okay, yeah. All right. Yeah. So here, but most people, you have the experience when you talk to your friends, if some algorithm program fast or not. Usually you use the execution time, right? Yeah. So you use the when you run the program, you use the execution time to tell you if it's fast or not. Yeah. So the first, so here, the first one, yeah, so here, first candidate in our mind is the execution time. Yeah. But the question, if it's a good measure or not, here I just raised the question, okay? Yeah. Here I just raised the question, yeah, because it's still a little early to talk about it. So we will discuss it later, okay? Here I just raised that question, yeah. Later we will come back to this question. Yeah. All right, next, are we satisfied with the solution? Are we satisfied with the solution? Because that's the only solution we know, right? That's the only solution we know. Now, if we know more solutions, then we can do comparisons. Yeah. Then we select the best one. But here we only know one. Yeah. So in order to answer this question, yeah, if we are satisfied with this solution, we need to think about, can we have other solutions? Can we have other solutions? Different solutions. Different ways to find the value of this polynomial. That's our next question. Yeah, yeah? So, yeah. All right. So here, if we have, or in other words, can we do a little better than the current solution? Yeah.
Are you asking us, like, if we knew all the values of all the terms in this polynomial, could we somehow be more efficient with the solution?
We know everything. Yes. Here, you can assume we get all the data needed. Yeah. The question, how do you find a better solution? Okay. Yeah. Right. Although a little abstract. Yeah. So here, I agree. Yeah. The reason many people, many of you do not feel very comfortable, yeah, because you see all those symbols, right? Yeah. You like to see now numbers, right? Then you can work. Yeah. But here, yeah, we do not work on numbers. We work on symbols. Yeah. That's the abstraction. Yeah. We human, we have that ability to handle the abstraction. Okay? Yeah. That's a good thing. That is a good thing. Okay? Yeah. We can do that abstraction. Okay? Yeah. We need that. Yeah. All right. So here, our next step, now, we want to see if we can do just a little bit improvement on this method. Yeah. Yeah. So even one tiny improvement, also good. Yeah. Because we want to see if it is possible to improve the solution. We want to see that. Yeah. All right. So next, in order to answer that question, consider some simplest case. Yeah. Yeah. Some simplest case. Yes. So here, do experiments. See, we use that strategy another time. Do experiments on simple data. In order to answer that question, yeah, let's do some experiment on simple data. Okay. So what kind of simple data here? Yeah, because here we want to see if we can do little better than our previous way. Yeah, our previous older way. Yeah, we did our older way. Yeah. Now we want to try, is it possible we can do slightly better, improve our previous way? Yeah. All right. Now, this monomial. Yeah, because this case still unknown, right? Yeah, case still unknown. Yeah. So when we do experiment, we want to work on some concrete k number. Yeah. Concrete k number. Yeah. Yeah. Then we feel better, right? Yeah. So this time we want to, yeah, this x to the fourth, so simple. We have the confidence to do something, right? Yeah, we have confidence. Well, this x to the fourth. It won't scare us, right? Yeah. So can you find a different way to find the value of x to the fourth with, yeah, you need a goal, right? You need a goal. Yeah. So here, what is our goal? Okay. All right. First, let's look at if we use our old way. Yeah. All right. So let me do here. If we use our old way to calculate x to the fourth, how many multiplications do you need? Old way. Yeah. This way. Straightforward multiplication. You do 1, 2, 3. Yeah. X times x times, x times x. 4 copies of x. How many multiplications? 4. 4. How many dots? One dot corresponds to 1 multiplication. How many dots? 3, right? Yes. Yeah. 3. All right. Not 4. Yeah. All right. 3. The reason you say 4 because here our answer is k, right? But the answer is k. We have a arbitrary coefficient number, a sub k. Then you need one more multiplication, right? A sub k multiply x to the k. You need one more multiplication. But here, our leading coefficient is 1. Our a sub k is 1. You can save that multiplication. You do not need that a sub k times x to the k. You do not need that multiplication. So you can save one multiplication. So use our old method, you need 3 multiplications to find x to the fourth. All right. Then we have a goal. Okay. After that, we have a goal. Can we do fewer multiplications than 3? Yeah. 3. Yeah. We already have. Okay. That's the bar. Okay. We can see it. But now we want to use fewer. Let's say 2 multiplications. Can we do slightly better than the old way? Yeah. That's our next question. Okay? You need to use some smart way. Yeah. Because this class, problem solving, yeah, we need to use our brain a lot to find smart ways to find solutions.
Efficiency maximizing solutions.
Yes. Maximize efficiency. Yeah. All right.
Sound like an economics professor.
No?
Maximizing efficiency.
Yeah.
Like that.
Yeah. Right. That's our goal. Okay? That's our goal. All right. But now, how to do it efficiently? All right? Yeah. All right. So here, let's do it in this way. Okay? All right. Multiplication. Let's do our first multiplication. X times x equals x squared. That's our first multiplication. Okay? 1. Our counting number 1. Then, next step, because our goal, we need to find x to the fourth. We already have x squared. X squared is known. That means it's in your pocket, right? You can use it. You can use it anytime. Okay? Yeah. All right. So our next multiplication. Now we will use a better way to do it. We take x squared times x squared. We can get x to the fourth directly. One more multiplications, we can find x to the fourth. Total 2, right? Yeah. So, oh, sorry. Yeah. Then the answer is 2. In this way, we can do better. Better than our first try. Yeah. Then we see some hope, right? We can do better. We can do better. Yeah. If we can find a smart way, we can do better. Right? Yeah. Okay, all right. Next. Analysis. Yeah. So now, we want to, because that's a very special case. Now we want to look at the general question. Yeah. How can we do better? Yeah. All right. Okay, all right. So here, as I said, in our problem solving, we rely on our experience, rely on our real world experience to give us inspiration solving problems. Yeah, we need that. So if you have a lot of real world experience, then that's a good thing for you. Yeah. All right. So, and here, if in problem solving, usually when at the beginning, when we do not have any idea, because at the beginning, we couldn't understand the problem well when we do not have any idea. Yeah. So there is one way people can do is the brute force method. Brute force. Yeah. Our first try, that's the brute force method. Yeah. No technique. For brute force, you just find a solution in a straightforward way, without any technique. Okay? Yeah. So that's the brute force method. All right. Yeah. Now we want to look at how much work do we need in the brute force method. Well, we want to look at the amount of work in the brute force method. All right. Yeah. Yeah. All right. So then, from there, we want to see if we can do better. Yeah. From the previous example, actually, we know we can do better, right? Yeah. Yeah. We know we have some room to do better. Yeah. But the question, the next question is there a systematic way to do better? Yeah. Because in our previous experiment, it's not a systematic way, right? It's just a special experiment. It's not a systematic method. So what do we need a good solution. The solution should be some systematic method. Yeah. That's the ideal solution, right? Yeah, ideal solution. All right. Yeah. All right. Now, first let's study the brute force method. Yeah. Study brute force method. So now we want to study two operations, additions and multiplications. These two operations. Yeah. So they're different. Yeah. So, all right. Yeah. So here, I talk about another important concept in our problem solving is because when we have many operations, another question related to a sequence of operations is the order of the operation. Yeah. That concept also very important. The order of the way you apply those operations. Now we know we have certain number of additions, certain number of multiplications, but when we apply those additions, multiplications, we have many different order to do it to get a correct answer, right? Yeah. Yeah. So there are different orders we can use to evaluate the polynomial. Then different orders may result different solutions. Different orders result in different solutions. Some solutions better than others. That's another step of our understanding. Yeah. So order is important.
So different order of operations results in different solutions, right?
Yes. Yes. Yeah. Right. Yeah. We change the orders, so very likely we get different solutions, right? Yeah. I would not say 100%, yeah, but pretty much 90-something percent. 90-something percent of the time, we get a different solution. You may not say 100%, right? Yeah. Yeah. It's very hard to get a 100% thing. All right. Yeah, so another understanding. Yeah. All right. So next, now we look at the execution time. Is it a good way to measure the performance? Yeah. Yeah. So here I want to talk about it. It's not a good one. Yeah. First, it's an objective measure. Yeah. Execution time, yeah, that's objective. Okay? All right. No problem, but it's unstable. Unstable. Why I say unstable? Yeah.
Where the instability is coming from? I thought our solution was like brute force.
Yeah. Right. Under different situations, you may get different execution times. Okay? Because you may use different machines, right? Yeah.
It's like a bipolar computer.
Yeah. Yeah. Right? Yeah. Yeah, because here we do not specify what computer to use, right? Yeah. All right? Yeah. So that's why we cannot say it is stable. No. No. All right? Yeah. Supercomputer, some people can use supercomputer, right? Yeah. Yeah. All right. So then, with the computer hardware, different computer hardware, that number could be different, although you execute the same program. So that's one thing. But even on the same machine, different programmers may write different code, right? Some code could run faster than other code, right? Yeah. So that's another. So from the software perspective, it's also unstable. Okay? Also unstable. So so this is not a stable measure, so we should want to find a better measure, stable measure. Yeah. All right. All right. So the stable measure, when you use different machines, different programs, you always get the same number. That's what we mean stable here. Okay? Yeah. It doesn't matter. Yeah. Always the same number. Yeah. All right. Yeah. So that number, we use number of additions and multiplication. We count number of additions, number of multiplications. On any machine, you use the same number of additions, same number of multiplication, right? Yeah? Yeah. So when you use different programs, you also need to use the same number of additions, same number of multiplications, right? Yeah. All right. Yeah. All right. But here, there is another difference we need to address. Yeah. Addition and multiplication, they are quite different. Yeah. In computer CPU, inside CPU, yeah. When you do additions and multiplications, which one uses shorter time, do you think? Addition or multiplication? Which one uses less time? Addition. Multiplication uses more time. Yeah. Multiplication uses more time. Addition, less time in computer CPU. Yeah. So we also need to consider that factor. Yeah. 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 So in order to make a fair comparison, because now when you have one addition and one multiplication, both number one, you cannot do fair comparison, right? Yeah. Because one multiplication is slower than one addition. Yeah. So in order to do fair comparison, yeah, we need to add some assumption, try to, level the battlefield. Level the battlefield. Yeah. So what kind of assumption we need to add? All right. Let's say each addition uses 1 unit of time. 1 unit of time. 1 unit. Okay, all right. Each multiplication then, based on the CPU, approximately the CPU needs 10 units of time to do one multiplication. 10 to 1 ratio. That big difference. That big difference inside CPU. Okay? Yeah. Yeah. Approximately. Yeah. All right? Yeah. So that's in this way, when we make this assumption, we level the battlefield. Okay? All right. All right. Yeah. Now we need to estimate the cost. Now, let me look at the time. Yeah, I have. All right. The subproblem 1, count the number of additions. Now we need to do the counting. Yeah. How many additions? We need to count number of additions. Do the counting. Okay? Yeah. All right. Here, let me introduce a counting method. Counting method. All right. So I do not ask you to try, because we did similar things before, right? We count number of terms. Do you think number of terms and the number of additions the same or not? Number of terms, number of additions the same or not? Any difference between these two numbers? Number of terms and the number of additions, same or different?
Yeah, I guess for terms we would like, using for multiplication or addition, but mostly for multiplication rather than addition.
Yeah.
Just adding.
Don't look at the multiplications. Only look at the number of additions. Yeah, you want to say something? No. Additions and the number of terms. Any difference? These two numbers. Yeah, what's the difference?
When you say additions, are you talking about the operators?
Yeah? Operations? Operations? Yeah. All right. You can see additions is 1 fewer than the number of terms, right? 1 fewer. Yeah. Actually, you can see each addition, one addition corresponds to 1 plus sign, right? 1 plus sign. One addition corresponds to 1 plus sign. Yeah. The number of additions is the same as the number of plus signs, right? Yeah. So when you count the number of additions, basically you count the number of plus signs, right? Yeah. The question, how do you count number of plus signs? Because here, now we have the problem we encountered in our first regular class, first class. Keep track of the data. Keep track of the data, right? Yeah. So here, when you want to keep track of the plus signs, you need to deal with that ellipsis. You need to deal with that ellipsis. How to keep track of all the plus signs? Get lost. If you do not have a good way, if you do not have some smart way, you get lost. Yeah. How to keep track of the data? Yeah. Here, let me introduce one method. Yeah. All right. Yeah. Yeah. So here, counting the number of additions. Yeah. All right. Right. So now we want to keep track of the data. Yeah. Okay. All right. Yeah. And we need some effective method to help us do that in this situation. Yeah. All right. Yeah. So now let me talk about that counting technique. Yeah. One effective counting technique. Yeah. Later we will use many times. So what's that counting technique? We call it counting by reference. The reason we get lost because we do not have any reference objects, right? No reference object. That's the reason we get lost. If we can find appropriate reference objects, then we won't get lost, right? Yeah. That's pretty much our real world experience. Our real world experience. Yeah. When you get to some new place, yeah, you may need some, reference, landmark, building, as your reference objects. Here, yeah, we do the same thing. Yeah. We need some reference objects. The essence of this method, we discover some one-to-one correspondence between two mathematical objects. Yeah. Because here, we are working on math formulas. Yeah. So we study mathematical objects. Yeah. All right. Here, I talk about the general method. We have object 1, object 2. And we need to establish one-to-one correspondence between these two objects. Okay, one-to-one correspondence. Okay? Yeah. All right. After that, yeah, then if we count the number of objects of the type object 1, it's hard to count. Yeah. Due to some reason, it's hard to count. Okay? Yeah. But if we, because they're one-to-one correspondence, now we switch our counting. We count number of objects of type object 2. Yeah. But we find it is much easier to count. Yeah. Can we just count the number of objects of type object 2? After we get the answer, can we use that same number as the number of objects of object 1? Because one-to-one correspondence, they should have the same number of objects, right? Yeah. That's the method. That's the idea of this method. Counting by reference. We use object 2 as the reference object for object 1. Okay? Here, what is our object 1? Yeah, our goal, we want to count the number of plus sign, right? So plus sign, that is object 1. Object 2, we need to find appropriate object 2. Okay? All right. Yeah. For the first plus sign, we need to establish one-to-one correspondence. The first plus sign, I want to map it to the A1, the subscript of A1 coefficient. Subscript, okay? Subscript is another object, right? Another mathematical object. So the first plus sign corresponds to the subscript of A1 coefficient. The second plus sign corresponds to the subscript of A2, that subscript. The last plus sign corresponds to the subscript of AN, A sub n. Is that one-to-one correspondence? One-to-one. Okay? One-to-one correspondence. Then, when we do the counting, yeah, if you count the number of plus signs directly, hard to keep track of, right? Yeah. Hard to keep track. Yeah. But now you switch to, you count different objects. This time you count the subscripts. You count 1, 2, 3. That's all your subscripts. Consecutive integers, right? So you list all the objects in type object 2. Okay, all right. Now you do the counting. How many numbers? How many numbers here? Subscripts. Do the counting. How many numbers? N. Yeah. N. Now you go back. Yeah. Yeah. Because based on our one-to-one correspondence, number plus sign should be the same as the number of subscripts here. Yeah. Here you can see I exclude the subscript of A0. I exclude it. Yeah. Because there is no plus sign before this A0, right? Yeah. There is no plus sign before this A0. So there is no one-to-one correspondence, right? No mapping. No such mapping, one-to-one correspondence. No. That's why we exclude it. Okay? Yeah. So this method, that's the counting by reference method. Yeah, very effective. Yeah. Later, in many other places, we need to use this counting method. Yeah. All right. Yeah. So today I go a little slow. Yeah. But all right. Yeah. But starting from next time, I need to go much faster. All right.
We went halfway through the solution.
What?
We were halfway through the solution to this example problem.
Solution, right? Yeah. Yeah. So this is the solution. This is, for this subproblem. Can you remember? I split our subproblem number 1. Yeah. Then our subproblem number 2. Yeah. Yeah. There we need to. Yeah. 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 Next time I try to, do a little faster. Yeah. Early because I need to introduce many simple methods. Yeah. Simple examples. Relatively slow, but start. We need to gradually go a little faster. All right. Yeah, that's it. Yeah.